Today we will discuss electromagnetic wave equation. Electromagnetic wave equation is a resulted of Maxwell contribution. Maxwell was the first person who collected all the equations of electric field and magnetic field. And as a matter of fact, four equations two from electric field and two from magnetic field collected and put at one place and tried to resolve the inconsistency. We have discussed these things in the last classes. And after this resolution of this issue of consistency in Ampere's law, he did some mathematical formulation. And that formulation gave, gave a very interesting result to the world, which known as electromagnetic equation. In this class, we will also study why this is so important. What is the significance of these equations for us? Yes, we have discussed electromagnetic induction, Faraday law, electromagnetic force. Then we have also discussed integral and differential forms of Faraday laws, self-inductance, mutual inductance. As an application of inductance, we have discussed the working of and principle of transformer and how energy can be stored. We have discussed this idea. Then we had discussed Maxwell displacement, current, derivation of Maxwell equation, electromagnetic field density, and Poynting vectors. Today we will discuss electromagnetic wave equation. The learning outcome of this lecture will be you will be able to learn how to deduce electromagnetic waves using Maxwell equation. Then we will also discuss significance of electromagnetic waves and how these waves are related with velocity of light. The electromagnetic equation is a second order partial differential equation that describes the propagation of electromagnetic wave through a medium or in a vacuum. These wave equations are similar to other wave equations. We have many things like heat equations, sound equations, and so many equations. But now this equations is little bit different because these calculations are deduced by electric and magnetic field, and then it is related with other light. So that's important. It is a three-dimensional form of wave equation. Following are the homogeneous form of equations. We have two types of forms, homogeneous and inhomogeneous. In this graduation classes, we are concentrating homogeneous only. In the case of homogeneous, the equations are like equations, symmetric equations in terms of electric or magnetic field. These are the equations. You see here nu is there, v is there, v square del 2 over del t2 of E is equal to 0, or nu square v square del 2 over del t2b is equal to 0. Where is like equations where this v square is equal to 1 upon mu epsilon. We will derive these things, we'll discuss, deduce these things. Previously here I am giving you the conclusion, the introduction about what are the equations. These are the equations, these are called electromagnetic equations in terms of electric field and magnetic field. This is generally called phase velocity in a medium with permeability mu and permittivity epsilon. But what is del 2? Yes, del 2 is a Laplace operator. Second differential. These are the differential equations. In a vacuum, this VPH is equal to C0. If you put the value of nu and epsilon 0 here, the value will be about 299,792,458 meter per second. A fundamental physical constant. I think all of you are aware with this constant. That constant is light, velocity of light. The electromagnetic variation equation derives from Maxwell equation, and in most older literature, B is called magnetic field density or magnetic induction. So now we will discuss how this can be obtained. But these are the equations. Somebody is asked what is equation? These are the equations. Before going into detail, what is the significance of these equations? First, we will discuss how these equations can be originated. From where you can get these equations. Obviously, as we have seen in the last slide, then these equations are depend on E and B. So somewhere you need equations in terms of E and B. And these equations can be obtained using Maxwell equations. Because in Maxwell equation we have four equations to explain electric and magnetic field anywhere, any system, any space. So we will discuss it. Full credit should be given to Maxwell for this. Maxwell was a fantastic scientist of that era in 1865, and he published a paper, Dynamical Theory of Electromagnetic Field. Maxwell utilized the correction to Ampere's circular law that he made in a paper in 1961 on physical lines of force. In the part 6 of this 1864 paper titled Electromagnetic Theory of Light, Maxwell combined displacement current with some other equations of electromagnetics, and he obtained wave equation with speed equal to speed of light. Here the catch lies. Here the contribution signifies. Maxwell did some work. Initially that work was not for light. Maxwell worked put for concluding all the electric and magnetic field equations, and he developed a theory in which he put all the laws of electric and magnetic field at one place. If we have four laws, first Gauss law of electric, Gauss divergence law for electric field, then Gauss divergence law for magnetic field, then Faraday law and Ampere's law. If we combine these four along with continuity equations, we can also use at some place, but four equations are four complete equations, necessary equations. In these equations, all first three equations, Gauss law for electric field, Gauss law for magnetic field, and Faraday law, these three equations are consistent. But he found that the fourth equation is not consistent. We have discussed this in last class. You can refer to that class where we showed how he added a particular term that is called displacement current in Ampere's law. So that is called modified Ampere's law. Finally, he used these laws, four laws, to obtain wave, electromagnetic wave. He did some mathematics that I will discuss in the next class, in the next slides. An important significance of this wave is when he calculated the velocity of that wave, he got the same number that we knew from a long time for a constant. We assume at a constant velocity of light. And the agreement of those results, the velocity of the electromagnetic wave is equal to velocity of light, seems to show that the light and magnetism are affection of same substance, and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws. He established an interesting concept that light is an electromagnetic wave. Light always is a matter of curiosity for all scientists. Since beginning in the 17th century, Newton started the work that light is a particle. He gave light corpuscular theory. Then at the contemporary scientist Huygens also gave a theory in which he discussed wave nature of light, and light become disputed, light become controversial even in the 17th century, when some is saying light is a particle and there is saying light is a wave. Do you know what is the reason behind this? Yes, because they did some experiments, and some experiment could be explained using wave nature, but they can't explain other experiments. So on the other hand, some concepts of wave can explain some light. If you assume light is a wave, you can explain some experiment. If you assume light is a particle, you can explain some experiment. But any concept can't explain all the experiments, like reflection, interference, diffraction. Interference and diffraction are having wave nature, whereas reflection or state motion are due to particle nature. But this Maxwell commented a different thing. He commented something on velocity and the actual behavior of the wave, that is electromagnetic wave. And this has given a new energy to study light again with new feature of the light. To obtain the electromagnetic wave equation in a vacuum using modern methods, we begin with the modern Heaviside form of the Maxwell equation. In a vacuum and charge-free space, the equations can be done in a particular way. We have shown those equations in the next slides. Maxwell derivation of electromagnetic wave equation has been replaced in modern physics education by less cumbersome method involving combining the correct version of Ampere's second law with Faraday's law of induction. The Maxwell equations are: first equation is Gauss law, del dot E is equal to rho over epsilon 0. But here, for the convenience, we have used charge free region, no charge is there. If there is no charge, then del dot E should be equal to 0. The second equation we have chosen, del cross E is equal to minus del V over del T. The third equation is del dot V is equal to 0. In some text we have used this as a second equation. So the del dot V is equal to 0 is always there. We know there is no magnetopole doesn't never exist. No magnetopole exists. So del dot V is always 0. So there is no modification here. And as there is no current there, so again one component is 0 in the amperes, and we have del cross B is equal to mu 0 epsilon 0 del E over del T. These are the four equations from where we are starting our journey. There are general Maxwell equations specialized to use with charge and current both set to 0. We have seen these equations in the previous slide. Now, to get the electromagnetic wave equations, what we will do? We will take the curl of the curl equation. What is the meaning of curl of curl? Yes, we have two equations. One is with del cross B, second is with del cross E. Now take curl of E and use mathematical identities to resolve this. Can we do this? Yes, we can. Here we have just taken curl of E and curl of B. If we just take curl of E, then on the right hand side you can write what is del cross E. We know this. Del cross E what is this? Actually this is minus of del V over del T. Yes, if you put this there and see, minus del V over del T can be done as del upon del T, and you can put del cross and the inside this. In place of del cross B, you can use something that is del E over del T. So you will get the information that mu 0 epsilon 0 del 2 E over del T2 using the identity. Similarly, if you use del cross V, then you can write this. In place of this, you can write mu 0 epsilon 0 del T here using the fourth equation, and in this you can use this. You can use this inside this as we did here, and finally you can put the del cross E is equal to minus del V over del T. You will get this answer. So these, now concentrate on these equations. These are giving you the values of waves. You may have question how we did this. Yes, we use these identities. Curl of V is equal to del of del V minus del to V. And we know this is 0 in both the cases, whether it is E or V. So all are 0. If all are 0, you will have this value only remain with this. And this we have used always with another identity. This is equal to this. We have used this in the previous. If you use this, you will get the equations as I displayed here. We have used del dot E is equal to 0 and del dot B is equal to 0 by assumptions. Del dot B is always 0. There is no problem at all. But del dot E, we have simplified this our equations. Del dot E is 0 when there is no charge in vacuum. So we have got these equations. 1 upon C 0 square, because we have taken mu 0 epsilon 0 as a 1 upon C 0 square. Del to E over del T2 is equal to minus del to E is equal to 0. Similarly, we can also write this equation in terms of B. 1 upon C naught square del to B over del T2 minus del to B del square B is equal to 0. Now, you may have this question in mind, and it must be, what is the use of these equations? You just see this. In the equation, you are getting this 1 upon C0 square, as we have discussed initially in terms of V. That is has the value C. So this is very interesting. If you put the value of mu and epsilon here, where mu is the speed, C is the speed of light, and mu is giving you the permeability, or epsilon is permittivity, then mu and epsilon, if you just put the value, you will get the answer, which is velocity equivalent to velocity of light in vacuum. Answer is close to this. So this gives a new updation to the light. The electromagnetic waves that we are discussing actually are light waves. We can develop many applications. Now, after this, he explained electromagnetic spectrum. He expanded light to electromagnetic spectrum, and now, along with visible section of the spectrum that is called light, we have long spectrum, very long spectrum from left to right, from infrared and UV and many other things. So it has very important significance for understanding the behavior of light. Take care.